Okay, good morning. This is John Heemstra. I'm Stephen Cornford, and today we're going to be looking at glaciology and meteorology in the Brecon Beacons. So here's the entrance to our site, which contains both some fascinating geomorphological features that John's going to be explaining, and then later on we're going to be going up a bit higher so that we can look at the effect of altitude on wind, temperature and pressure. Okay, so we're standing here in the Brecon Beacons, and this is going to be a beautiful, bright, sunny day. There's a high pressure system over the whole of the UK. But here early-ish in the morning, we're still seeing quite a lot of low level cloud, and particularly behind me here, you can see something called a radiation fog. And these occur because for a period in the morning and overnight, the air temperature is actually colder close to the ground than it is a little bit higher up, and that tends to trap that fog and that cloud low down. Okay, so air doesn't like to rise from cold to warm, it likes to rise from warm to cold. And so the radiation inversion is a sort of classic piece of evidence, or the radiation fog rather, is a classic piece of evidence of those inversions occurring during the day. Within an hour or so, it'll probably have gone and that fog will have evaporated away.
Right, we have arrived at Craig Cerrig Gleisiad, which is in the central Brecon Beacons. And the reason for being here is that we want to demonstrate some of the glacial geomorphology in this landscape. So I'm standing here on the complex of ridges, and with a certain origin, and your task is really to find out the depositional history of the area. Obviously, I'm going to give you a few clues, and so to start with, the reason why Brecon Beacons is quite interesting is because it was glaciated at different stages in the past. The last major glacial, which was around 20-25,000 years ago, this whole area was covered in ice, a big ice sheet that ran from northerly sort of direction south, and which reached all the way down to the Gower Peninsula. So that was where the ice limit was. So consequently, this area of the Brecon Beacons was under ice. Clearly, after that, the climate got warmer, and in that time, the ice retreated, and more of the land was exposed. But at some point, around 12,900 years ago, there was a return to colder conditions, and that period that started at that point is called the Younger Dryas. And the Younger Dryas is also referred to in the literature as the Loch Lomond Stadial. Why a return to colder conditions? Well, there are several theories about it. One of the most prominent ones is referring to ocean currents in the North Atlantic, where a large input of fresh cold water basically sort of disturbed the currents that normally transfer heat from the equatorial region up north. So that is one of the most prominent theories explaining the Younger Dryas. So this Younger Dryas period, that cold snap, that lasted for about 1,500 years. So and that if you think about that theory of closing down the oceanic heat transfer. That was about the time that it sort of re-established itself, and the climate got warmer again. But that period of 1,500 years was enough to bring back small glaciers and small snow patches in upland areas. And obviously the Brecon Beacons is one of those upland areas. This is just about high enough to be able to support marginal glaciation. And there is evidence in the landscape for those small glaciers that reformed, and that is what this project is all about. So I said earlier that we're standing on a set of ridges here, and that is the main evidence to be able to reconstruct these small bodies of glacial ice. Sometimes, well, obviously you know that glaciers form through accumulation of snow, and then slowly but surely it builds up, and then maybe it can convert at some point to ice as well and start flowing, and that is when how a glacier is defined. But sometimes that flow of ice isn't actually achieved, and then in those cases you're just left with an accumulation of snow. And still, those accumulations can actually produce ridges like I'm standing on here now as well, or very similar to those that I'm standing on here now. So we're really in the sort of marginal conditions climatically for either glaciers to form or not.
Okay, so here I've got a really useful piece of field kit. It's a portable weather station, and it will tell me about the wind speed and direction, about the temperature, about the pressure, and about the humidity. And the first thing that stands out on it, today's a very high pressure day, and the weather forecast had the pressure in Swansea and also the pressure in Brecon around 1037 millibars. But this meter is measuring 985.9 millibars. So is there something wrong with the meter or something wrong with the weather forecast? It's a much simpler thing than that. We're about 430 meters above sea level. And one of the things we know is that atmospheric pressure drops by about 12 millibars for every 100 meters you climb, at least close to the surface. And that relationship between pressure and pressure and elevation is so well known that the aircraft we can hear above us is almost certainly using that relationship to gauge its altitude. The other thing that's different from a bit lower down is the temperature. It's about 3 degrees Celsius colder here than it is at sea level, and that's one of the reasons why elevated regions like the Brecon Beacons become glaciated. But as John has explained, this is a marginal region for glaciation, and so we're keen to think about how it could be colder and how perhaps more snow could accumulate in an area like this, which we believe was glaciated. So you can see a tall cliff behind me. This is a fairly sheltered region, and the meter is measuring a wind speed of only a few knots on this admittedly calm day. We would expect the wind to be faster at higher altitudes and the temperatures to be lower. And snow that forms on these high altitudes will readily be blown into this hollow, where the shelter will cause it to drift and lie. So later on we're going to go up this hill and we're going to measure that pressure difference. We're going to see if our theory is right. We think that the pressure should drop by another 25 millibars as we move up, and the temperature might drop by 1 or 2 degrees Celsius as well.
Okay, so we're in an area of marginal glaciation, and I told you before that that the evidence that remains in the landscape are small ridges, and these ridges tend to occur next to escarpments, and you will see in a moment where we are positioned, and so we'll illustrate that quite nicely. Behind me, you can see a ridge. And if you go a bit further over in that direction, you see that the ridges are a part of a complex. In fact, some of the ridges are quite high, up to tens of meters. The one that I stand in front of is not quite that high, but the fact is that this location is actually quite complex in terms of its depositional history, the glacial history. These ridges occur generally in a position next to escarpments, and I'm just moving a bit now. As you can see here, there's a large ridge which is in the order of 160 meters high, very steep, and this is actually what we call a head wall. So this head wall is where snow may have accumulated. So there's a depression behind that head wall, and in certain conditions you get an accumulation of snow that can actually sort of turn into a glacier. And the ridges that we're standing on is the end product of that glacial action. The ridges are moraines as we know them, and these are the pieces of evidence that are left in the landscape. Okay, so a bit more about this complexity in this location. I said we're standing on a moraine, and people are agreeing on the origin as a moraine for this particular ridge. But if you look at the drone footage, you will see that there are several sort of areas with quite a bit of complexity in the ridges. There are in general, in this sort of landscape, two types of ridges that you can identify. There's the glacial moraine that we're standing on now, and that is formed by active glacier ice flow. Material is falling onto the glacier, makes its way into the glacier slowly but gradually because more snow is added on top, and then at some point it may end up at the base of the glacier where it is sort of modified and moved forward, and it may re-emerge at the snout of the glacier, and that is where a ridge may be formed, and that is what we call a moraine. So if you look at the material in the moraine, you can actually pick out clasts that are modified. They are sub-rounded to even rounded material. Much of it is striated. So in other terms, clasts and material is being modified under ice. I mentioned that in some cases snow may accumulate and it may not quite reach the stage where ice is formed and where it starts to flow. And in those cases you're left with what we call a perennial snow patch. And these perennial snow patches may actually produce ridges as well. So in front of the snow patch, just like in front of a glacier at its snout, you may also get an accumulation of material that has fallen onto the snow patch and basically slid over it and is accumulating in front of it. So in those cases, the material ridges are called pronival ramparts. So ramparts, other word for ridge. Pronival means in front of a nival sort of body of material, which is snow. So pronival rampart produces ridges as well. So those are the main two types of ridges that you see in a landscape like this. There is a further sort of element of complexity, and that is probably visible from the drone footage as well, and that is where obviously in a glacial landscape there's a lot of instability. There's a lot of meltwater around, and you can trigger slope movements quite easily. In fact, what you see behind me here is evidence of more recent slope movement. It's now quite vegetated, but you can see there is a talus cone behind me, so illustrating that slope movements are quite common in this area. And as you can imagine, in a glacial landscape there may be slope activity associated with the formation of moraines, with the formation of pronival ramparts as well, and that is a bit of an introduction to the complexity of this location in particular.
Okay, so we've walked a little bit further up the ridge, and the meter here is telling us that we're now at an altitude of 455 meters. Okay, we've gained 30 meters, and it doesn't have a GPS or anything like that in it. It's worked that out by considering a change in pressure. Okay, so the pressure has dropped to 983 millibars. Not much, but enough for the meter to know that we've moved up by about 30 metres. So you might think, well, why do we care about pressure? Atmospheric pressure doesn't tell us much about snowfall directly, you may think. The reason that pressure is important is because gases, as they move to lower pressures, cool. So if you ever put your finger on a bicycle valve and let the tyre down, your finger would have got cold, and that's through a process called dry adiabatic expansion. Okay, so it's that change in pressure as we move from low altitude to high altitude that's one of the major mechanisms that's responsible for the change in temperature. So we'll go a little bit further up and we'll see what pressure variation we measure at the summit. So now we've walked nearly to the top of this summit. It's a little bit higher over there, and we've got a considerable drop in pressure. So the meter here is now measuring 962.8 millibars, so that's about a 20 millibar drop from the site we were at earlier. So that's associated with the new altitude of 631 meters it's reading at the moment, but it's actually fluctuating a little bit. Okay, so the measurements are probably precise to around 3 or 4 millibars. You have to be careful of that. Now, the other thing that's happened as we've moved up the hill is that it's become colder. Okay, so the temperature here is 5.8 degrees Celsius, and that's a good bit colder than it was just a little bit further down the ridge. It's slightly warmer than it was when we talked down in the dip, and that's because it's later in the day. The sun has been heating up the atmosphere. So if you want to measure the temperature difference over a small altitude like this, or a small altitude change like this, you really need to have two stations. Okay, so one here at height and one in your reference location. We would be able to compare this with the weather station, for example, at Mumble's Head, but that only produces readings around every hour, whereas this meter will produce for us, will log readings every 5 minutes or so. So a good experimental design would make use of several of these meters to form a network at different altitudes. Now, the other thing that's changed as we've moved up the hill is wind speed. Okay, so I'm just going to start measuring wind speed now. So at the moment it's reading around 6 or 7 knots, but the wind speed changes considerably over every second. You can see that the wind direction is changing a little, and it will probably change a bit more if I moved away from it. And the wind speed is fluctuating as well. So when you're measuring wind speed and when you're measuring wind direction, you need to take an average over about 10 minutes. Okay, but subjectively we can clearly feel that it's much windier here. So up here we would expect snow to be blowing. Okay, it wouldn't accumulate here through drifting. Instead, it would drift down here in the depression where we think the glaciers would form. So the view behind me is quite different from what we've seen over the rest of the day. We've now got a large flat plateau stretching to the south and west, and this is the sort of area where falling snow would accumulate and then be blown by the stronger winds up here to fall over the edge to our north and east, and then accumulate in those on the northeastern side of those hollows. So that completes our picture of where we think the source of snow is at this site.
Okay, so we've arrived here at the top of the head wall, and there's a drop of around 160 meters behind me, and we've come here just to point out some features in the glacial geomorphology. The light isn't ideal, but you can see things because of the vegetation patterns. You can see a few ridges that are picked out by the bracken as opposed to the green of the grass. So the area down there, that's where we were earlier, where the moraines are. There's a series of parallel ridges that you can pick out from the vegetation patterns. But I said it's much more complex than that. In fact, if you move over in that direction towards the road, you can see a big lobe of sediments that is all associated with a slow slope movement. So as I pointed out earlier, slope movements can be associated with the glacial landscape, and that is a big lobe of material that is thought to be of slope movement origin. In fact, if you go the other way, there are a few ridges that you can pick out by the vegetation patterns again, and that is a different phase of landslides, of topples coming from that side of the head wall, maybe associated with the glacial activity and maybe not.
Okay, so that's all of the things we wanted to talk about in our Brecon Beacons glaciology and meteorology day. We've talked about the glacial settings and the evidence in the landscape, moraines, but also the complexities of mass movement. And we've talked about meteorology, the relationship between pressure, temperature and wind behaviour with altitude, and the relationship there with blowing and drifting snow that we think is an important part of the way these glaciers form. And the assignment for you involves synthesising those two components to form a coherent picture of the glacial setting here.